Hi, welcome to our lecture on models involving logarithmic and exponential functions. Now, we've seen some models already. We talked about compound interest, radioactive decay, and last lecture we even looked at a fairly complicated model involving the heights of men and women. Today I'd like to show some models a little more complicated perhaps, or more interesting, involving the exponential and logarithmic functions. Now, this is a tough topic because models often might seem very simple because it's difficult to explain a complicated model in such short time. So you'll have to bear with me if the models look kind of naive at times. But then I'll show you some models also that are very, very accurate, and hence they'll have some ugly numbers in them. Perhaps the simplest model of all that is used in applied mathematics is the exponential growth model. And in its simplest form, it's the function y equals ae to the bx. A and b are constants to be determined by the model being considered. X is the variable, and b generally is greater than 0 if you have exponential growth, and if b is less than 0, it would be exponential decay, as in radioactivity. And in fact, the simplest of all these models of exponential growth would just be y equals e to the x. But now we'll massage it a bit and accept models of the form ae to the bx. Here's our friendly graph of e to the x, and the graph of ae to the bx, where a and b are constants to be determined, will look somewhat like this graph. Okay, let me show you a simple example. This example is very, very simple, so you might complain a little bit about how the numbers come out. But I want to illustrate the idea of how to model with an exponential equation. Suppose you have a research experiment going on and you have a population of fruit flies, and it's increasing according to the law of exponential growth. And suppose after 2 days you count the flies and you have 1,000. And after 4 days you count them and you have 3,000. So according to this model, how many flies will you have, say, after 5 days? So let's explore this model. We're going to assume that the fruit flies grow as the exponential model, ae to the b, and I won't use x now, I'll use t because time. So we'll use ae to the bt. And we have some equations we can form because we were told that at time 2, there were 1,000 flies. So when t equals 2, y is 1,000. And also when t is 4, y is 3,000. So we plug those numbers into the model. 1,000 equals ae to the 2b, t is 2, and then 3,000 equals ae to the 4b. Okay, 2 equations, 2 unknowns. Maybe we can solve for a and b. Let's try to do it. Okay, the first equation, 1,000 equals ae to the 2b, I can solve for a in that equation in terms of b and get a equals 1,000 divided by e to the 2b. Now take the second equation and plug in this new value of a. So 3,000 equals ae to the 4b, but instead of a, put in 1,000 divided by e to the 2b times e to the 4b. So now I have an equation with just the unknown b. Good, let's simplify it. The 3,000 and the 1,000s cancel to make a 3. And remember that exponent rule, e to the 4b divided by e to the 2b, you subtract the exponents, don't you? So we're left with e to the 2b on the right-hand side. Okay, 3 equals e to the 2b. What's b? It's hiding up there as an exponent. Bring it down to earth. Take logs of both sides. The log of 3 would be the log of e to the 2b. By the inverse properties, that's equal to 2b. Divide by 2, and we have the value of b. It's 1/2 log 3. Good. We got one of the 2 constants. What about a? Well, go back to the equation for A as 1,000 over e to the 2b and plug in this value of b. It looks a little messy, but some nice cancellations will occur. A equals 1,000 divided by e to the 2b, and instead of b, I put 1/2 log 3. Don't panic. It's not so bad. The 2 and the 1/2 cancel, don't they? And you're left with e to the log 3. Oh, inverse functions. You're left with just 3 in the denominator. How pleasant. A is nothing more than 1,000 over 3, or approximately 333.33. Good. Here's our model now. We know the A value. It's 333.33. We know the B value. It's 1/2 log 3, which on my calculator tells me it's about 0.5493. So my exponential model for this situation is 333.33 times e to the power 0.5493t. Okay, so there's our model. Not a very pleasant model. We asked the question, what happens after 5 days? Plug in 5. When you plug in 5, and with your calculator, you determine that you have about 5,196 fruit flies. Let's look at a picture of this model. Here I've used a graphing calculator to graph the curve, the model that we just derived. Notice some of the features of this curve. At time 2, when t is 2, the model says that y is 1,000. When t is 4, the model is 3,000. And the answer when t was 5 is 5,196. Here's a question for you. Oh, by the way, before I do the question, notice the shape. It's our exponential growth, isn't it? That looks like the exponential function. Here's a question for you. What was the initial population of fruit flies? What did we start out with? Well, look back at the model. When t is 0 in this model, you get e to the 0, which is 1, and so y is nothing more than 333.33. Now, you can't have a third of a fruit fly, so it's approximately 333. So in this picture, the curve goes back and touches the y-axis at about 333. There's something else you might notice here, kind of an interesting sidelight. Look how this model works. At time 0, there's 333. 2 days later, it tripled to 1,000. 2 days later, it tripled again to 3,000. You could say that 2 days is the tripling time for this model. Kind of neat. It's kind of like half-life, but now it's tripling time. Speaking of half-life, let's turn to carbon dating again. In a living organism, in organic material, it turns out that the ratio of the content of radioactive carbon isotopes, that's carbon-14, that ratio to the content of non-radioactive carbon isotopes, carbon-12, is approximately 1 to 10 to the 12th power. In other words, there's not much radioactive carbon. However, when the organic material dies, true, the carbon-12 content remains the same, but the radioactive carbon, the carbon-14, begins to decay, and its half-life is 5,715 years. So that's kind of how carbon dating works. Let's look at a specific example. Suppose you have a 4-gram sample of carbon-14. So here we are, 4 grams of carbon-14. How much will you have after 1,000 years? How much carbon-14 will you have after 1,000 years? Let's solve this problem. Well, our model is radioactive decay. It's exponential decay. So we'll use the same formula, y equals ae to the bt, but we expect b now to be a negative number, don't we? All right, what's a? Well, a is the initial amount. When t is 0, e to the 0 is 1, so I know a is 4 right away. The only question is what's b? Let's solve for b. I started with 4. The half-life is 5,715, so when t equals that number, the amount is 2. So I have the equation 2 equals 4 times e to the power 5,715b. And now we solve this for b. We've done this before, haven't we? b is hiding up as an exponent. Let's bring it down to earth. How about if I first divide by 4 and I get 1/2 equals e to the power b times 5,715. Take logs of both sides. You know the dance now, I think. And the log and the e cancel, and I have log of 1/2 equals b times 5,715. Divide by that number, and we finally have the value of b. It's approximately minus 0.0001213. That's an approximation of the quotient log of 1/2 divided by 5,715. Notice something here. It's a negative number, isn't it? Thank goodness, because we have decay going on. Log of 1/2 in the numerator there is a negative number, isn't it? Remember, log of 1 is 0. But if you're below 1, in between 0 and 1, logarithms there are negative. So thank goodness we got a negative answer. So we now know the model. The model for radioactive decay of carbon-14 is given by y equals 4e to that power, to that exponential power, that decimal power. And to find out how much radium you have, not radium, carbon-14 you have after 1,000 years, plug in 1,000. With your calculator, you determine it's about 3.54 grams. You started out with 4, and after 1,000 years, you've still got a lot. You've still got 3.54 grams. Here's a picture again of this situation, and I did it with a graphing calculator. Notice that at 1,000, we have about 3.54. We started at 4, and then it decayed off. And I've also plotted the half-life. When time is 5,715, we have 2 grams. Okay, let's turn to a new class of models. Gaussian models. These are really neat, I think, and a little more complicated, unfortunately. These are commonly used in probability and statistics, and they represent populations that are so-called normally distributed. That basically means the population is in the shape of one of those bell-shaped curves. In a minute, I'll show you a picture of a bell-shaped curve. So what do these models look like? Well, they involve the exponential function and some constants. And here is the general model. Y equals AE to a certain exponent. And this exponent's a little ugly. It's minus x minus b squared divided by c. So there are 3 unknown constants in the Gaussian model, A, B, and C. One of the most popular or well-known Gaussian models is when A is 1 over the square root of 2 pi. In a minute, I'll tell you where that came from. And then B is 0 and C is 2. And that would be 1 over square root of 2 pi times e to the power minus x squared divided by 2. Here's a picture of that curve. That's a picture of the model I just talked about. It's that normal distribution. It's the distribution perhaps of heights of humans. Some of them, the average height's in the middle, and then over to the right, the humans are perhaps taller. There's not as many over there, and then not as many shorter. And the average is right in the middle. And an interesting fact about this curve, the area under that curve and above the x-axis is precisely 1 unit, 1 square unit. Okay, so let's do an example or a model using the Gaussian model. Here we go. Maybe you've taken the SAT test. I took it when I was younger, an unpleasant experience. And the scores of the SATs are published, and it turns out that in 2005, the SAT math scores for college-bound seniors roughly followed a normal distribution. They roughly followed a bell-shaped curve. And here was the bell-shaped curve for the SAT scores that year. And how did they get this model? Well, they knew it was going to follow a bell-shaped curve, and they had all the data, and a computer then generated the model. It's kind of a messy model because this is a real-life application. This is based on true statistics. And here it is. Y equals 0.0035 e to a power, and the power is minus the quantity x minus 520 squared divided by 26,450, and x is between 200 and 800. And that's the range of SAT scores, between 200 and 800, at least back in 2005. I like to tell my students the following when I do this. It's sort of a bell-shaped curve, and the average scores there is the high point. And then you have students off there to the right, and the students off to the right, I like to say, are the University of Florida students. And then you have a few students over there on the other side of the average score, and I like to call them the University of Georgia or Florida State students. It usually gets a laugh from my own students, but I don't think my rival universities think it's very funny. All right, good models so far. Good models. Let's turn now to a model that appears a lot in calculus books now. It's called the logistic growth model. And again, it's an exponential function that describes a certain kind of growth pattern of a population. The logistic growth models are usually used when you have a population that might grow very, very quickly for a while. And then the growth rate kind of levels off. It doesn't grow as fast. That could be due, for example, because the population runs out of food. So it grows real fast, and then, hey, there's no more food left, so the reproduction rate goes down. Or there's not enough room. They fill out the petri dish, and the bacteria can't grow anymore because there's no room for them. So these patterns it has a low rate, and then it grows real quickly, and then it kind of levels off again. And the function that describes this behavior is, again, not so pleasant, but it's of the following form. Y equals A divided by 1 plus BE to the minus RX power. So it's a function of that form, and A, B, and R depend on the data. Okay, let's do an example of the logistic growth model. And I'd like to do an example dealing with college students. Again, you might think this is too simple, but it illustrates how you can use this model. And in a real life situation, the numbers wouldn't be quite as nice, but the principles would be the same. So suppose the following scenario. This, by the way, is a true scenario. Suppose you have 5,000 students on a college campus. University of Florida is 50,000, but this is a small college. 5,000 students. And after vacation, one student comes back with a flu virus, a contagious flu virus. And this student begins to infect other students. Sitting in the classroom, coughs, and other students start getting sick. Well, many times this kind of contagious disease will be modeled by the logistic growth model. And in this case, the model turns out to be 5,000 divided by 1 plus 4,999 e to the minus 0.8 t, where t is non-negative. So let's assume that's the model for the spread of this virus. Again, how did we come up with this model? The data would come up with those numbers, but let's just accept those numbers as being the model. So why is the number of students infected after t days? For instance, how many students are infected at the beginning when t is 0? Well, plug in 0 into this model. Let's see what we get. E to the minus 0.8 times 0 is e to the 0, which is 1. 4,999 times 1 plus 1, that's the denominator, it's 5,000. The numerator is also 5,000. So in the beginning, one student has the flu, and that's what we said. One student comes back from vacation, starts coughing, but in the beginning, this student was the only sick student. Well, how many students will be infected after 5 days, say? Let's find out. According to this model, all you have to do is take t equals 5 and plug it into the equation. So here we go. The model was 5,000 divided by 1 plus 4,999 e to the minus 0.8, and now it's times 5. And then you multiply that out, use your calculator, you discover that the answer is about 54 students. So the one student comes back, starts spreading the virus, and within 5 days, there are about 54 students infected. And then it starts getting worse. Here's a graph of the number of students infected at time t. I've plotted the point 554. That's one of the bottom points there, because in the beginning, not many students are infected. But as more and more students become infected, everybody's becoming contagious. And now the infection really gets bad. And for a while, there's a growth rate there, a very high growth rate of infection. And then near the end, it starts leveling off again. Now, this is kind of a frightening model, because if we look closer, let me ask you this. What's the horizontal asymptote to the right? What's happening when we get back, say, at time 20? What's happening here? Well, let's look at the equation. When t is large, e to a negative power, a large negative power, that term goes basically to 0. And so you're left with 5,000 divided by 1. In other words, this is a frightening virus. Every student gets infected, according to this model. Don't ask me what this virus is. It's kind of scary, but that's why it's kind of a simple example. But the rate of infection is very high for a while. It levels off, but basically every student is going to get infected because there's a horizontal asymptote at 5,000. Kind of scary. But again, trust me, these models of logistic growth occur all over biology. This is a very common example in biology courses. Now, you've probably asked, and I've talked about it a little bit, how do you come up with these models? And a lot of it is fitting data to curves. And this is tough stuff. My science departments and engineering departments, biology, statistics, etc., are full of modeling courses. This is big business in applied mathematics. And now with computers, you can do much better modeling than you could, say, 30 years ago. Some models come from the law of physics. And I'd like to show you a final model that comes from the laws of physics. This model actually is a model from calculus courses. In fact, when I teach calculus, I always do this model. It's one of my favorite problems in calculus. Now, we won't be able to do the calculus portion of this model, so you'll have to kind of take my word for it a little bit. But you'll understand the equation I come up with here. So this is based on what's called Newton's law of cooling. And again, it's one of my favorite problems. Here's how Newton's law of cooling works. The rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium, the room temperature. For instance, you could be baking a pie, and it comes out of the oven at 400 degrees, and you put it on the table, and your room might be 70 degrees. 400 minus 70 is a pretty big temperature differential, so it's going to cool pretty quickly. But the rate of change of temperature is not constant. As the pie gets cooler and cooler, the rate of change lessens because the pie's temperature is closer to the temperature of the room. Now, what I do when I teach calculus is I bring in a coffee cup. I bring it in, say, full of coffee, and it might, say, be 100 degrees, my coffee cup, and I put it on the table, and I measure the temperature. I have a device that you can put into the coffee, and it'll show the temperature of the coffee at various intervals. And I can actually flash it onto the wall so all my students can see the temperature of the coffee. It starts at 100, and then it goes to 99, and it starts going down. And it obeys Newton's law of cooling. Okay. In my calculus class, and I'm sorry this is not the calculus class, but again, take my word for it, you can use calculus to derive the model for the cooling of my coffee cup. And here's what it turns out to be. The temperature turns out to be 60 plus 40 e to a certain power. And that power is, again, kind of ugly. The exponent is minus 0.02877 t. Again, a real life problem has an ugly number in it, an ugly decimal. But look at some of the features of this model. What's the temperature when T is 0? Okay, when T is 0, e to the 0 is 1, 60 plus 40 is 100. So the model kind of makes sense already. When I begin, the coffee's at 100 degrees. And now that's a negative exponential, isn't it? So that term, 40e to that negative power, will begin to decrease, won't it? It'll get smaller and smaller. That's because the temperature's going down. So here's a graph of the temperature of the coffee. And this is the kind of graph my students would be watching during the calculus class. They would see this apparatus measuring the temperature and then putting the results on the blackboard behind me. And they would see the temperature at time 10 would be 90 degrees in this model. And then at time 20, it might be 82 degrees, and it gets lower and lower. Notice that over there at time 0, it's at 100 degrees. Now, of course, depending on the room temperature and things like that, the numbers might be slightly different, but this is sort of what happens. And while the students are watching the temperature go down, I'm doing the mathematics required to derive this model. And it uses Newton's law of cooling, and it uses calculus. But here's the final result, this equation we had. Let's talk about some of the features of this equation. We've already observed that when t is 0, y is 100. What happens when t is very, very large? Mathematically speaking, what's the horizontal asymptote to the right? Well, look, when t is very, very large, the exponential term dies off, doesn't it? It starts to disappear. And y turns out to just be 60. What's that 60 mean? Well, that's the temperature of the surrounding room. When I lectured that day, it was cold. It must have been wintertime. And it was 60 degrees in the room. So the coffee cooled from 100 degrees and got closer and closer to 60 degrees, obeying Newton's law of cooling. Something else kind of neat about this model. Notice that in the first 10 minutes, the temperature went down 10 degrees, 100 to 90. Did it go down 10 degrees in the next 10 minutes? It only went down 8 degrees. How come? Well, the differential of temperatures is not as large anymore. It used to be a 40-degree differential between the coffee and the room. But after 10 degrees, it's now a 30-degree differential, so the rate of cooling is less. Okay, nice model, I think, really fun. The good news is, when you finish this pre-calculus course, you'll be ready to take calculus, and you'll see this kind of model actually derived using calculus skills. Okay, congratulations. We are now through with our lectures on exponential and logarithmic functions. Now, we aren't through with those functions. They'll come back again throughout the course, but we finished pretty much the portion of pre-calculus that is often called algebra. Remember I said that pre-calculus has another name sometimes called algebra and trigonometry. Well, we've sort of done the algebra part, and now we're going to turn to trigonometry. And that is really the core of this course almost. I mean, we're going to spend about 13 lectures on trigonometry, and then after those lectures, we'll be using trigonometry in other places. The trigonometric functions are another class of functions, just like polynomials, rational functions, logarithmic functions, exponential functions. Now we'll have trigonometric functions. And needless to say, they are crucial for success in calculus, science, engineering, and pretty much all of applied mathematics. So I look really forward to the next few lectures when we begin to study trigonometry. I'll see you then.